electronics aimed at the motorsport level. Modern motorsport electrical systems will almost always include one or more network communication buses, either for the transmission of data between parts of the system or programming of the various ECUs present in the vehicle. For the transmission of data between devices, CAN bus is the most common network used, and the wiring requirements are covered in our Wiring Fundamentals course. These requirements don't vary at the motorsport level, but if the network bus does need to run alongside electrically noisy wires or close to ignition components, the use of shielded cable is a good way to add a factor of safety. Ethernet is another network bus that you will strike when wiring automotive electronics aimed at the motorsport level. It is the same networking protocol used by the computer industry, however, we usually stray slightly from the standards to make our bus wiring more suitable in an automotive environment. An Ethernet bus consists of 4 wires: transmit positive and negative, and receive positive and negative. Because the bus transmits and receives on different pairs of wires, it's what's known as full duplex, meaning it can both receive data and transmit data at the same time. The networking standards employed by computers call for a cable to be used that has 4 twisted pairs of wires, making 8 total. The extra 4 wires used are for higher speed data transmission and not often needed in an automotive installation, so they are usually omitted. To form an Ethernet network of more than 2 devices, we need to use a network hub or switch. This device monitors the traffic on the network and directs it where it needs to go. This is a key point of difference to the CAN bus network, where every device can see all the data on the bus. In an Ethernet network, data is sent in distinct packets that have a specific destination and will only end up at that destination. Ethernet is more commonly used for ECU programming and configuration rather than data transmission between devices, and for this reason it's common to wire the Ethernet pins of a device to an easily accessible connector in the vehicle, so a connection to a laptop can be quickly made for programming. I tend to collect up all the Ethernet and CAN buses together into a single diagnosis and programming connector mounted on the main switch panel of the vehicle. I then create a single programming cable that breaks the buses out to the required connectors for interfacing to a laptop or diagnostic equipment. When we build a dedicated motorsport wiring harness, our choice of materials becomes simpler than when we build a club level or modified streetcar harness. To withstand the harsh motorsport environment, we will only use the best materials with the highest specifications. Many of the materials we use are borrowed from the aerospace industry, as the design objectives of this industry are a good match for our professional motorsport applications. This does drive the price of a motorsport wiring harness up substantially, but this higher price is preferable to chasing electrical problems in the pits under the pressure of a race event. We'll look at the key wiring harness elements now and outline the materials that we're going to use. The primary element in our wiring harness, as the name suggests, is the wire itself. When building a professional motorsport wiring harness, we will always use Tefzel wire. Tefzel is actually a trade name for the insulation material used on this wire, which is ethylene tetrafluoroethylene that then undergoes a radiation treatment process called cross-linking. The end result of this is a wire that has a thin, tough insulation jacket that can withstand temperatures as low as negative 65 degrees Celsius while still remaining flexible, and as high as 200 degrees Celsius without melting or charring. This wire is often referred to as Spec 55, which is another brand name specific to Tyco Electronics. When you're searching for this wire, however, the most useful term will be M22759/32, as any wire meeting this specification will be fit for our purpose. The thinness of the insulation jacket does mean we need some specialised tooling to work with this wire, which we will cover later in the practical section of the course. This insulation jacket is also resistant to any chemical we're likely to encounter in the motorsport environment and has a smooth, low-friction surface, allowing the wires within the harness to move against one another without chafing. As mentioned in the power supply design section of the course, often we will select the size of wire we're using based on the connector specification that the wire needs to run to. running an extra wire in a situation where a larger current handling capacity is required rather than stepping up to a larger size of wire. As important as the toughness and chemical resistant of the insulation jacket on the wire we use is, the same elements of the sheathing we use to cover our bundled harness are even more critical, as it is the sheathing that will bear the brunt of the exposure to the motorsport environment. In fact, one of our main aims when we are constructing a motorsport wiring harness is to completely seal the wires within the sheathing to ensure that they are protected. We exclusively use Raychem DR25 tubing to sheathe a motorsport wiring harness, as its chemical resistance and operating temperature range of minus 75 degrees to 150 degrees Celsius make it ideal for this application. This shrinkable tubing has a recovery ratio of 2:1, making it easy to install on our harness sections, and it retains its flexibility when recovered, ensuring our completed harness also remains flexible. As DR25 shrinks to its fully recovered dimensions, its wall thickness increases, giving us excellent abrasion protection also. Where our wiring harness needs to branch out to connect to various electronic devices, we seal these transition points using specific molded heat shrinkable shapes that recover tightly to our harness sections and then become rigid as they cool. While recovering these molded shapes, we use an epoxy potting compound to seal the interface between the DR25 outer surface of our wiring harness and the molded shape, ensuring the wires within our harness remain completely protected from the environment. As these molded shapes become rigid after they're recovered, they offer excellent strain relief to the transition points and offer us an ideal place to locate splices and adjust the ordering of the wires in our concentric twist layers. It's a similar situation where our wiring harness is terminated to a connector. Here we also use molded shrinkable boot shapes to seal the connector back shell, retaining the integrity of the harness and providing strain relief to the connection points, giving us further locations also to perform those splice joins.